Welcome to the deep dive. Today we're getting into the nuts and bolts of what's next for large language models. We're doing a deep dive on the DeepSeek R2 framework. Our mission is to figure out how it's getting this frontier level AI performance, and not by just making the model bigger, but by building it smarter. We're looking for those deep structural and algorithmic changes.
Exactly. And for you, the listener, the big idea here is what they're calling intelligence density. It's all about how much reasoning power you can get for every bit of compute you use. It's a direct response to, the fact that you just can't keep making these things bigger. You hit a wall,
Hardware ceiling?
a hardware ceiling, and some pretty catastrophic stability nightmares.
Okay, let's start right there with reliability. Because when developers try to widen that information channel with what they call hyperconnections, they just hit a wall. The signal explodes, training runs crash. It's a mess.
Right. And R2's solution is, well, it's elegant. It's called manifold constrained hyperconnections, or MHC. It's a structural guarantee. It forces those connections onto a very specific mathematical space to restore signal integrity.
Like a governor on an engine.
That's a great way to put it. It's like installing a mathematically perfect governor that stops the engine from redlining and blowing up.
Okay, but hold on. I saw the data point on this. It says this drops the signal deviation from, almost 3,000 down to just 1.6. That's incredible for stability, but it adds a 7% compute overhead. Is that trade-off actually worth it?
Oh, absolutely. I mean, 7% is tiny compared to the cost of a failed training run, which can waste weeks of time and a fortune in energy. So you're trading a tiny bit of performance for near-perfect reliability. It's a massive win. It lets them iterate so much faster.
So the foundation is stable. Now let's talk about the engine itself. We always think of the transformer architecture as this sort of, a typewriter for thought. It's sequential.
And that's where R2 is experimenting with something really different. We're starting to see these post-transformer paradigms emerge. They're exploring something called recursive cognition lattices.
Lattices, so not a straight line.
Not at all. Think of it less like an assembly line and more like a web. It allows for multiple parallel abstract thought processes at once. And crucially, they get rid of self-attention completely.
Wait, they abandon self-attention? That sounds radical. Isn't that the core of how transformers work? Are they losing something critical there?
It is radical, but the results they're reporting are astronomical. We're seeing claims of a 400-fold improvement per TFLP in inference efficiency. And it's unlocking new capabilities. I mean, they're using this to design things like simulated room temperature superconductor structures.
Wow.
Yeah, that's a huge leap from just pattern matching to something that looks more like genuine cognitive simulation.
Okay, let's bring it back to something practical. Memory. How does R2 handle ultra-long context, like 128,000 tokens, without needing a supercomputer's worth of RAM?
They use a technique called multi-head latent attention, or MLA. Instead of keeping these enormous key and value vectors for every attention head, MLA, it compresses them.
Into what?
Into a single, shared, very compact 512-dimensional vector. It's a clever trade. A tiny bit more computation to save a massive amount of memory bandwidth. They're cutting memory reads by almost 29 times compared to the standard way of doing it.
An incredible hardware saving. Okay, let's shift to alignment. We've talked a lot about how AI alignment is often just this, opaque score, a single number. How does R2 learn human values in a way that's maybe more transparent?
This is really interesting. They've moved from that single score to something called generative reward modeling. So instead of just getting a good or bad score, the model is trained to generate its own free-form critiques. It actually explains its reasoning.
It coaches itself.
Basically, yes. They call it self-principled critique tuning. It learns to critique itself based on principles it generates.
And what's the payoff for you, the user?
A nearly 50% drop in hallucinations on reading comprehension tasks. The model doesn't just know the right answer, it demonstrates an understanding of why it's the right answer. So if you pull it all together, R2's real power is in optimizing the whole stack. You've got the structural guarantees from MHC, the new architecture with the lattices, and then the resource optimization with MLA.
And the biggest implication here, for you, the listener, has to be the economics. R2 is getting performance that's on par with the big closed-source models, but at a tiny fraction of the cost. We've heard rumors of an input token cost of just 7 cents per 1 million tokens.
It completely changes the game.
It really does. This whole focus on doing more with less, like the 83% model size reduction that lets it run on edge devices, it suggests intelligence is moving. It's shifting from this big centralized utility like a power plant to something ubiquitous and distributed. Which leaves you with a final thought to mull over. What kind of revolutionary applications become possible when this level of state-of-the-art AI can run affordably directly on the hardware you already own?